To present to the group. Chris Chambers is the CEO of Sirius Simulations. I'm the VP there for technology, and we really do appreciate the opportunity to show you what we have done in the last 2 years. Our company is only just now almost literally 2 years old. So, Sirius Simulations, and the technology we'll be showing you tonight is wireless VR, which I've just managed to step out of the way of where I should be, but nevertheless, we'll have this. I've been walking around the room already showing some people off. We describe this, just as an introduction, as a head-mounted display in a box. This is an HMD like any other HMD. The only difference is it's packaged differently. But every HMD has a screen, it has a battery, there's some electronics in there, and in this case, because it's wireless, we've got a wireless receiver in there. But other than that, if you package this differently, you could put it in front of your eyes and you'd have an HMD. In this case, we call it an HMD in a box, thanks to this very nice $25 box from Office Depot. Okay, so we'll talk about the technology and what led us to this. I want to give you just a quick introduction to the company itself to describe why we went down this path, because our initial start was not necessarily down that path. We're a Florida-based, veteran-owned company located in Orlando. Many people outside of the simulation and training business don't know that Orlando is the center of the universe for that type of technology. There are more defense companies located in Research Park on the east side of Orlando next to the University of Central Florida that are there specifically to deal with the agencies of the military that are there, both the Air Force, Army, Navy, Marine Corps, and others that are located there. They do all their contracting there for any training that is based on simulation. So our technology, we're used to it, you know, those of us, the gray-haired guys have been around for a while, we tend to think of this as simulation, and the more modern term is virtual reality. But the technology is the same. We design and manufacture human motion-based mixed reality training devices, especially in the area of individual and small group simulation training. We'll talk about that in a second. We lease and sell complete training systems, and this is important because we started off with the intent of making a complete training system. I'll show you an example in just a moment. And the HMD aspect of it, the video aspect, that was a component of what we needed to do to deliver our full training systems. We have a veteran-heavy team just because of the nature of our business and a lot of business experience in this area. These are just some examples of different game engines applied for that purpose. Our focus is on dangerous task training, any sort of situation that you need to train in simulation because it's too dangerous or it's impractical or it's totally unacceptable to train. The example I like to use is you can't train a locomotive engineer to know what to do if someone steps out on the track in front of them. You just can't tell a human to step out in front of a moving train. So if you're going to do that sort of thing, you've got to do it with simulation. So that's the focus, and in order to do that, we emphasize on the realistic side of things. So we use natural human motion, typically camera-based motion capture systems, and the person that's the trainee in the system sees himself in an HMD in a virtual world where that person is embodied as an avatar in the virtual world, but as he moves left, right, up, down, kneeling, rolling, whatever he does, that's all repeated and captured in the virtual world. So here's an example of the types of things we do over here: hazardous training, soldier training, firefighter training, those types of things. We like to use the phrase that reality is wireless, so virtual reality should be wireless. Another phrase we use is you can't do this wired, but this is an absolute requirement for a soldier training system. For those of you who may not have been through that type of experience in the past, what the Army teaches its soldiers is if you're under combat fire and you go down on the ground, you don't get back up where you went down. You roll and you get back up in another spot so that if someone saw you go down, they can't just expect you to pop back up in that same location. So therefore, for that type of training, it is essential. You have to do this roll. You can't just say, well, we're going to leave that out because the wire gets in the way. You can't do that. It's an unacceptable aspect of the training. So we have to deal with that. And that will show up if you were a buddy in the world looking in a 3D view. That's the character that's rolling. Here's the live character, of course. And if you see yourself, you would see a view something like that, you know, just from the rear. The types of products that we focus on are, as I said, Sirius Simulation. The name comes about from Sirius-based training. Mounted and dismounted combat soldier training, special operations training, similar applications for police and fire. emergency services, and some SWAT and other specialty areas. Okay? This is a complete training system that we make. We refer to it, call it by the name Ready to Train. It is a squad set, a squad meaning a group of generally 9 in the Army, and here are 2. In our small space that we had at the time, we only had room to set up 2 training systems, but we can see here that there are cameras that are set in these towers, and then the cameras are able to pick up the markers that are just set on with Velcro onto the uniform. But the trainees are able to train in their real uniform with their real combat gear, with their real or simulated weapons, because we also instrument weapons and people can come in and use the real thing. So the realism is very, very important to us. For that reason as well, we cannot use any kind of man-wearable or backpack computer. Soldier comes to training as he's getting ready to go to combat. So he comes in, he's loaded up with gear. He's not going to say, oh, well, take off all your normal gear and put this computer on. The Army tried that. It cost the taxpayers $92 million to find out that it didn't work. After about 3 years, the system was jettisoned. It's out there on eBay probably somewhere if you look. The basic components of the system as we put it together, just to roughly describe it, there's an instructor-operator station where one instructor can watch everything and control and manage the training environment. There's something we call an individual training cube, which just means an area. These are deliberately rather small just because it's a demo space, but nevertheless the trainees are free to move around in that area. They're also free to move across a larger area. So for instance, the one concession we have to make to something that's not totally realistic is we put a small thumbstick controller on the weapon itself. So if you want to march down the road for 3 miles, you can just push that button and do that, even though your physical space is not that large. The head-mounted displays that we put together, this is a prototype early version photograph right there. But the types of head-mounted displays that we do are required to have peripheral vision involved. We put 2 1080p displays in front of each eye, or 1 per each eye. That gives us 3840 by 1080 resolution with binocular overlap for true 3D vision in the middle. In addition to that, it's all wireless, so we're able to accomplish that, and the wireless audio and the wireless data that goes along with it. It's specifically made to mount onto a soldier's helmet with a standard night vision goggle mount, and it's counterbalanced on the rear with a battery and whatever electronics are required back there. And then, as I said, we can add markers to weapons and instrument the weapons and do the same sort of thing. So, the peripheral vision is required because in the types of training systems that we are emphasizing and delivering to our customers, peripheral vision is required. And this is a clear example. This is not exactly to scale, but nevertheless, this is what you would typically see with most HMDs on the market. 60 to 70 degree field of view, that sort of thing. You'd come up on a roof and you'd have a view of something like this, but in fact you may have a threat that's very important to your life that you need to know about and deal with. It's within your normal peripheral vision, but might not be within the range of what a head-mounted display, or at least not what a typical head-mounted display could show you. The world's widest field of view and highest resolution wireless HMD is something that we have invented. Again, this is a mock-up that we went through, a 3D printed version to show different ways of putting it together. We experimented with different mounting methods and that sort of thing, but this is a device that we make today. Then we come to something that we invented and patented, which we call the video reformatter. And the point of the video reformatter is we needed a way to rotate an image in real time. The reason we needed to do that is because, first of all, we had to deal with things wirelessly. And we had the great idea, like a lot of people in this world have had this great idea. They said, wouldn't it be cool if we could just take a cell phone display, because these things look good and they're cheap. What if we just take that thing and turn it on its side and put that in front of someone's face, and there we'll have an HMD. We'll put some plastic around that and this will be great. It is a great idea. And a lot of people have gone down that path, but what they run into very quickly are some fundamental technical limitations, and that's what I want to describe to you as to why we did this. The primary purpose of the reformatter is to rotate an image in real time. In other words, to do it literally as fast as the pixels are coming in from the source. And this eliminates the latency that has typically been associated with wireless applications. Pardon me. And that latency will generally lead to uncomfortable use, but quite often will lead to nausea. Okay? So why is this necessary? Well, when we put this stuff together, we realize, first of all, that there are a number of wireless devices on the market already, and these carry the video signals wirelessly. They were specifically designed to meet the demand to support televisions. The idea, some years ago when those devices were designed, was to make it possible for you to have a big TV on the screen, on the wall at home, and not have a bunch of wires running to wherever your cable box and all that sort of thing is. And they work very well for that. So this demand was foreseen by a group called the Wireless HD Alliance, companies like Panasonic and others that are part of that group. And they established something called the Wireless HD Standard. Basically, it does a great job with the normal television, etc., and it can carry 1080p video from a source to a television or other display device. The problem is when you try to adapt that into what we call virtual reality, people moving around, engaging more, they weren't really designed for that, and we run into some problems. These devices were designed specifically for a TV of a certain era. As a general rule, their highest performance is 1080p. So, as you know, things like the new Oculus and other devices are different resolutions than that, generally higher resolutions. TVs are natively landscape devices, meaning they're wider than they are tall. They're meant to drive that format and to accept that format. And therefore, the wireless video devices commercially available today generally have a maximum performance in the range of 1080p at 60 frames per second. But a critical limitation is that they're in landscape mode only. They will not do that resolution in a portrait mode. Well, guess what? These are natively portrait devices. All of them. The whole billion of them they make every year for the cell phone industry are natively portrait. So, a couple of quick images to show what I'm talking about. Hopefully it won't be too boring. Here's a basic landscape image we'll start off with as our example. And then let's look at that if we were to just chop it off or turn it up without changing the image in any way. Well, if we just simply, rotated the device and cropped the image to fit, we would get something like that. Now, obviously, when you take your cell phone and you turn it on its side, the thing's got a sensor inside, it knows that you've turned it, it can rotate the image in software. That's all fine and dandy, but it's slow. You don't realize it, but you would if it were head tracked and you were turning your head and you get the lag associated with that. So let's look again. Well, what if we had that image and we put it on the cell phone type image where we physically rotated the display on its side, but if we took that same crop thing we had before, well, now we got another problem because now the image is longer than what the source was, and now I got a big black area, and obviously that's, an even worse mess. Okay, so to describe it in a little more detail, in landscape mode, the pixels are illuminated in order along the long dimension of the screen. So this red one is the first pixel that comes in, and then this is the second one, the third one, and you go down the row this way, and then you fill in the second row, and you keep going 60 frames per second, filling in the image in that order. Each new frame starting the scanning up there in the upper left corner. And as I pointed out, TVs and computer monitors work like this. So now we look in portrait mode and we see that it's a different situation. The pixels are now illuminated along the short dimension of the screen. So now we still start up here and we go across like that, but we're putting fewer pixels across before we start over and we go again. So it's no longer at 1080p, it's not 1920 across and 1080 down. It's 1080 across and 1920 down. So we have to deal with that somehow. But this is how these cell phone displays work. All right, so when we look at a natively portrait device, even though we turn it on its side, that doesn't change the electronics inside the thing. The raw device is still working in the exact same way. So what happens now is the pixels are still filled in from left to right, except now it seems that they are going down to up. They're going this way because I've turned the thing on its side. And then they're going that way. So the device is still functioning the same, but the order and how it affects the image is different. So what we're trying to accomplish is we had that original landscape image and we want to rotate that and make it fit on a natively portrait screen. This has been done for years. I don't know when this was figured out. I should have looked up or tried to Google and find out, but I'd bet it's 30, 40 years people have been doing this. But it's typically done by pulling in a frame of video into memory, processing that with software or firmware, and then sending it out to the screen. So let's look further at what's involved in that. So we'll consider this rotation in software the traditional way. We'll buffer the memory, buffer the image into memory, and then rotate it in memory and then output that screen. Next slide, please. Here's the first problem. The very first pixel that we need to feed to the portrait device is that one, because it scans this way. But the image is coming in this way. So in other words, the first pixel I need is the first pixel at the start of the very last row of what's being sent to me. Therefore, I have no choice. I don't know what this pixel is. I don't know if it's blue, red, green, what it is to form this image. So I have no choice. I have to wait. So we must wait to receive that yellow pixel before we can even start the image rotation process. And this is the fundamental issue. That guarantees you at 60 frames per second that you will wait 16 milliseconds of time. 16 milliseconds of time is enough for to throw the human brain out of whack. If you're turning your head and that image is following you at a minimum of that. Remember, that's the minimum, because you also have the processing time of the computer, the processing time of the application, the game engine, the tracker, every other thing that goes on in a VR environment. But if you take this approach, you've guaranteed that you've got 16 milliseconds in there that you sure wish you didn't have. Okay. So then we come to our reformatter. Now this slide basically says what I already just walked through. And that is, if we start with an image, transmit that across a wireless link. That sort of doesn't matter whether it's wired or wireless. But if we get that across here to a receiver and then we rotate it in software, we will recover the image and we can display it on a portrait device. But it will happen 16 milliseconds later than what we want. 16 milliseconds. Essentially, that's unacceptable time for what we wanted to accomplish. Is, though, that we've accomplished the whole process inside the time allotted for one frame of video. Therefore, we call it zero frame latency because there's no latency from one frame to another. Absolutely none. Next slide, please. Another way of looking at this is if you do a little simple math, you can say, what does the reformatter do versus software-only frame buffering? Again, this is just a different expression of what I've been saying so far, but if you take 16.7 milliseconds and divide by 17.6 microseconds, roughly speaking, it's an order of 1,000 times faster than what had been previously available. So at this point, having a reformatter do real-time zero-frame latency image rotation for us, that means we can use commercial off-the-shelf wireless devices, which have been around for years but have not been suitable for this purpose. And we can now use them with portrait mode display screens inside of an HMD. We do that for our own HMD. We already have a couple of small companies that make their own custom HMDs for entertainment systems and specialty environments. Not the Void, but those kind of places I'm sure you're familiar with. Anyway, there are companies that are using our technology now and building that into the HMDs that you would wear if you go to those locations. So the result is a wireless HMD. There's no additional latency compared to the same HMD wired. I'm sure you all know, none of this is speeding up your computer. None of this is speeding up your graphics card. None of this is speeding up your game engine software. You still have all of that, and everybody needs to make all that go as fast as it'll go. But we can't fix that. That's not our area of business. The only difference is we're doing it wirelessly, so there is the time it takes for the signal to be transmitted from the transmitter to the receiver. Those commercial wireless devices typically report that they do that in less than a millisecond. So again, that's getting it down from 16 milliseconds for us to eliminate the frame latency and then let the wireless system, if it adds on 1 millisecond, that's okay. Okay, next slide, please. I wanted to at least sort of end our presentation tonight by talking a little bit about where we're going. Everything so far has been talking about what we've done and why we did it. The future of wireless VR for our company and where we're headed and headed commercially, first of all, is higher video resolutions and higher video frame rates. The reason for that is, as I said, our first iteration was to solve this problem for 1080p devices. And there are a zillion of them out there. We got lots of screens, lots of companies make these things. We can buy them. Our customers can buy them. They can build their own HMDs. They can do a lot of clever stuff. But that doesn't get us to serving an HTC Vive or the new Oculus or something like that that's running at 90 frames per second and different frame rates. And so, reading between the lines here, one might say this is headed right down the line towards the HTC Vive and the Oculus and all that. How will it work? Well, it's a secret for now because we haven't, finished all that. And availability, the best I can say is soon. We're not talking, years. It's going to happen in my lifetime. It's going to happen soon. So we hope to, see you all again at another event, perhaps where we will be showing off another level of technology. Okay? And then I think we have one slide left. And this we did earlier this year as a proof of concept. So you see Chris, he's outdoors with a laptop, and Mike in our office has got an Oculus DK2 on, and we enabled that thing wirelessly. We took that also to a small VR show in Los Angeles and showed it off, and that was kind of fun, especially since we were just around the corner from the Oculus people, so they got to see that as well. But nevertheless, it was just a proof of concept. And the reason we were able to do that, for those of you that, interested in these details, is the DK2 ran at, I think, 75 hertz, 75 frames per second, 74, something like that. But you could run it at 60. It had a mode where it would run at 60. So, and it had a 1080p screen in it, and therefore it fit the requirements and, the capabilities of what we did and what we had. So we simply made it run at 60, and we, rigged it all up, hooked a battery to it, etc., and went outdoors and demonstrated wireless VR with that. Later on in the evening, we'd be pleased to show you what we have and let you ask all the questions you want, but I hope some of the questions may have already been answered in the presentation. I hope it's been interesting for you. Again, thank you for your time.
We got time for one question. Who's got a question? Anybody? Military VR, wireless VR, the future? There's one. Oh, go ahead. No, that's fine. I know this guy, he's a podcaster, he asks a lot of questions, so I'll let you go.
So my question is, how do you feel about the new FCC thing where they basically have, I guess, some wireless spectrum that they're released so it's, basically anyone can use?
Yes. There's a band of 7 gigahertz between 57 and 64 gigahertz, roughly. It's commonly referred to as the 60 gigahertz band. The FCC allows unlicensed use of that band up to a certain power point. So as long as basically you're running low power devices, you can do anything you want. That's wonderful. You don't have to go get a license. You don't have to have a lot of equipment certified. You don't even have to qualify yourself as an experimenter. You can do whatever you want. And we will, in fact, take advantage of that in some of our products. As some of you may know, the only disadvantage is the 60 gigahertz, this very high frequency millimeter wave kind of signaling. That stuff is, generally speaking, line of sight. These commercial devices get around it by having the steerable beam and the transmitter and the receiver communicate, and they, the thing bounces off the walls and the floor, and it eventually says, oh, I got a good signal here, and then it stabilizes, and that's fine. And that really, truly does work great. But when you say you're in a VR, this thing that was assumed to be a television on the wall that was stationary is not that way anymore. Now it's an HMD on a person's head, and they're walking around. So it's more challenging, and that is some of the challenges that we're facing. But yes, the FCC's grant of that space, and by the way, that's legal all around the world. There's some variations, but generally speaking, in every country you can use that space unlicensed. And therefore, a lot of people are moving in that direction. It's just a technical challenge to deal with.
Are your products going to be targeting the consumer market, the enterprise market, or both?
Well, the enterprise market certainly to start. We are a very small company, so we don't have the scale capability, the manufacturing production scale, etc. Now we are dealing with suppliers like anyone else does in the U.S. and elsewhere that we could scale up, but the nature of our business and the nature of our customers is our HMDs and the things that we make for our own training purposes will, at least initially, always be at the top end, and therefore they'll be expensive, definitely by comparison to consumers. But a lot of the consumer companies have expressed interest in what we're doing, and they would have the scale and the production bandwidth to be able to do bigger and better things, perhaps by licensing some of what we do.
All right. Thank you, Damon.